Hello. Today I will be presenting my paper titled Context Aware Mamba-based Reinforcement Learning. This is the outline of our presentation. We'll go over the context and the problem statement of social robot navigation. Then we'll talk about the system architecture of CAMRL and how we decided to use deep state space models. We'll then go over the simulation setup and talk about the results of our testing. Finally, we'll discuss some future directions and ongoing works. Social robot navigation is about solving the problem of making a robot navigate through a crowded environment in a socially acceptable manner. In social robot navigation, the environment is composed of a robot and a crowd. A simple visualization of the social robot navigation problem is given on the figure on the right. The goal is to optimize the robot's path by minimizing the time to reach its destination, avoiding collisions with other agents, and limiting the duration spent within human comfort zones. Moving on to the deep reinforcement learning framework. Deep reinforcement learning for social robot navigation typically has two differentiating blocks, the crowd state encoder and the value/policy network. The state encoder processes the crowd data encoded in the joint state of the system, which includes all the observable information of the environment, including the robot's complete state and the other agent's hidden observable state. The value/policy network determines the next action of the robot. Social robot navigation literature has mostly focused on the state encoder block, where it has used methods like self-attention and graph convolutional neural networks to model interactions between the agents and the robots. However, very little focus has been given to the value network, where a typical value network has been modeled using a simple multi-layered perceptron. Moving on to the state space models, they are widely used in econometrics, finance, control systems, and robotics to model dynamical systems. Recent attempts to combine state space models with deep learning have resulted in strong performances with long range dependencies. They have shown to be faster than transformers in inferencing and quicker than recurrent neural network in training. Mamba, a recent deep state space model presented by Gu et al. In 2023, has been chosen for this study. So now let's talk about why we are using deep state space models. A reinforcement learning algorithm that is capable of long-term planning is one of the central goals of reinforcement learning. The 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 ability of deep state space models to handle long-range dependencies and handle large contexts opens new possibilities in reinforcement learning. Given that the optimal value function is a causal system that is dependent on previous states, it makes sense to use a neural network that can model a sequence of states instead of a simple multi-layered perceptron. Moving on to the system architecture. Our solution combines deep state space models with deep reinforcement learning, and it performs better. It In our experiments, it performs better in certain matrices than existing solutions like CADRL, SARL, LSTM-RL. The diagram shows how CAMRL computes the next action of the robot. Based on the deep reinforcement learning framework shown earlier, this contains the crowd state encoder. The GRU encoder layer and the value network, which contains the bulk of the computation. One key differentiator in CAMRL from other planners is that it considers the state across a time horizon t as its input. The behavior network outputs a value vector containing values across the time horizon t. The value at the current time step is used to determine the action that the robot takes through an epsilon greedy policy. This is incorporated into the next time step of the simulation and the cycle continues. This diagram shows the entire deep reinforcement learning scheme, including the training paradigm where we use deep V-learning introduced by Chen et al. In 2017 alongside the first deep reinforcement learning planner in social robot navigation, CADRL. Moving on to the setup for training and testing. Setup was based on circle crossing with some improvements. Circle crossing can be seen on the right and is a typical simulation environment in social robot navigation. Training was done on a simple circle crossing environment while testing was done with four sets of varied scenarios from the diverse four dataset. This helps improve the rigor of evaluation since these varied testing environments are a better representation of the real world. The environments are divided into large and dense environments over circle and square formats, which can be seen here. Here are three scenarios: circle crossing, large square crossing, dense square crossing. Three more based on other permutation of the crowd size and dimensions were used, namely simple square crossing, dense square crossing, large circle crossing. We used social force model and optimal reciprocal collision avoidance ORCA to simulate the crowd. Let's move on to the metrics. These are the standard metrics used throughout the social robot navigation literature. They include success rate, which is the total number of times the robot successfully reaches the goal over the total number of tests, the time taken to reach the goal, collision rate, which is the total number of collision over the total number of tests, and the discomfort percentage, which is the ratio of time for which the robot the comfort zone of an agent against the total time. The comfort zone is defined by the radius extended around each agent representing social comfort. In our experiments, CAMRL performed better in terms of success rate, collision rate, and discomfort frequency. While the agent does not perform well in terms of timeout against its closest competitor, SARL, it does manage to maintain a low collision rate, which means that instead of colliding, it might take a longer route or detour, which prevents it from reaching the goal on time. However, still keeping it socially compliant by not running into other agents and doing a better job at staying out of the comfort radius of other agents with only a 7% discomfort frequency. Moving on to the conclusions. In this work, we proposed a new type of deep reinforcement learning planner for social robot navigation, namely CAMRL. CAMRL performs comparably or better than other deep reinforcement learning planners. This warrants further investigation and demonstrates promising potential for the use of deep state space models in social robot navigation planning tasks or otherwise. So now let's talk about some of our ongoing and future works. So we are currently in the process of comparing CAMRL with more modern models such as graph-based learning approaches, such as relational graph learning and attention-based interaction graph from Chen et al. And Liu et al. 2020 and 2023. We want to incorporate real-world demonstration by testing CAMRL on TurtleBot 3 and train the model using different learning algorithms, for example, PPO and DTPG. And for our future works, we want to add more realistic scenarios to the simulation, including a more realistic method of simulating the crowd other than ORCA and SFM. And we would want to use different crowd state encoders, for example, self-attention and other graph-based methods. These are our references, and thank you.